Good morning. Today we're going to take a look at all the different ways that the Earth is on the move. You're going to find a quiz posted in Blackboard. Please remember that we are still in the pale blue dot module, and this will be under day 5. Your questions are going to be the following. What is the actual shape of the Earth? I want you to give one piece of evidence that supports the shape of the Earth and differentiate between two things. Differentiate between theories and laws. What are the differences between a theory and a law? Let's take a look at this picture in front of you. I see the sun, I see the Earth, and I see the moon. We are going to take a look at all of the different motions that are being represented in this picture. But first, let's see how much you already know. So what phenomenon causes the Earth to experience night and day? Is it 1, rotation, 2, rotation around the sun, 3, revolution, 4, the moon, 5, the position of the Earth and the sun? If you chose rotation, you are correct. As the Earth rotates upon its axis, we experience night and day. So brings me to my next question. What happens to the stars during the day? When it's daytime outside, why don't we see stars? A, they're still there, but the sun outshines them. B, they're on the other side of the Earth. C, they are hidden behind the sun. D, we can't see them due to clouds covering them. E, not seen due to the Earth's position in space. Did you guess A? If you selected A, you're correct. They are still there, but the sun is simply outshining them because it's so much closer to us than the stars. And yes, of course, the sun is a star. But in this question, I mean the other stars other than the sun. So let's take a look at the Earth's motions involving rotation. First of all, the Earth has an imaginary axis at the center of rotation. So you could take a knitting needle and put it through a grapefruit for a model. If you could figure out how to do that with a beach ball, either one would be good models. But then the knitting needle could represent the imaginary axis. And the fact is, the Earth spins once every 24 hours and 56 minutes. And we call this one day. It also spins faster than you think. The Earth rotates at a rate of 1,609 kilometers every hour. That is fast. Did you know that the Earth spins from west to east? All right, that's counterclockwise. We are spinning from the west to the east. The Earth has a tilt, so the axis isn't straight up and down. The Earth is actually tilted roughly 23.5 degrees on its axis. So how exactly do we know any of this? Well, I want to talk to you about this. First of all, we have something called star tracks. And star tracks, if I can get that to come up, star tracks, you can see those in the photo. And those are basically the nightly movement of stars in the sky. And star trails or star tracks reflect the Earth's rotation on its axis. And the Earth rotates a full circle relative to the backdrop of the stars in a period of about 23 hours and 56 minutes. So, if you set your camera to capture something like that, this is what you would see. You would see that trail of stars in the sky. So that's one reason that we know that the Earth rotates on an axis. What's another reason? Foucault's pendulum. I think this is so cool. Let me see if I can get it to come up. Well, I can't. So I'll talk more about the pendulum in just a minute. Let's talk about the direction. How do we know the direction? Well, we know where the sun rises. It rises in the east, which means we are rotating from the west to the east. That's why West Virginia sees the sun first and California sees it 3 hours later, because we are moving from the west to the east. Now, let me see if I can there we go. So here we have an example of Foucault's pendulum. And if you know what a pendulum is, you just swing it. You pull it back and you let it swing. A pendulum swings back and forth. That's it. Back and forth. But if you have a large enough pendulum, and I don't mean like large in the weight of it, but a long pendulum, let's say about 4 or 5 stories tall, and it drops down, the weight of it is down at the bottom, and you swing it back and forth, then in 24 hours, you will see every little of those dominoes knocked over. But why? Well, back in 1851 in Paris, Foucault used a heavy iron ball on a 60-meter wire, and he set that pendulum swinging north to south. Now, a pendulum is not going to change its direction. It has one set motion. So when he pulled it back and set it going north to south, he found that it changed 11 degrees every hour in a clockwise direction. Why is that? Well, let's think about it. What is the only thing changing? The pendulum itself is still going north to south, north to south. It doesn't know the difference, but what is changing is that the Earth is rotating. The Earth is rotating, and therefore those little dominoes or those little chips get knocked down every hour because of the rotation of the Earth. I wish I should bring one in or a video of one to show you. And how do we know that the tilt of the Earth is correct? And we can measure that because of the amount of light in various places on the Earth. As you move north or south in latitude, the amount of light varies. And that's how scientists were able to calculate the tilt of the Earth at 23.5 degrees. But has it always been like this? Has a day always been that long? Has a year always been that long? And the answer is no. Rotation on the Earth's axis is actually slowing down. And it slows down at a rate of 2 milliseconds every single day. So, what is that doing to the length of a day? Well, it's making it longer. It's making our days longer as rotation slows down. Sorry. So what's the evidence? Well, we have atomic clocks on the Earth, and cesium atoms undergo radioactive decay at very regular intervals. So the radioactive decay isn't changing, but the rotation of the Earth definitely is. There is also evidence in something called rugose corals. 375 million years ago, we had corals that had monthly growth rings. And what scientists were able to calculate is that a year, 375 million years ago, was actually 440 days long. So why would that be? Well, we had much shorter days back then. It didn't take us as long to rotate once upon an axis. So let's move forward. Let's take a look at a day in the park during the Jurassic period. So that's roughly 201 million years ago. Well, during the time of the Jurassic, during the dinosaur days, a day on the Earth was 23 hours long, and a year was 385 days. That means that in 200 million years from now, our days will be about 25 hours long, but our years will only last roughly 335 days. Crazy. Is it any big deal? Probably not to us. And so why is it happening? Well, the moon, the gravity from the moon is slowing us down. What else? Well, it really harms our GPS communication satellites, our power grids, and anything else on the Earth that relies on accurate timekeeping. So those sorts of things need to be reset. So tonight, don't forget to set your clocks ahead 2,000ths of a second before you go to sleep. And of course, every day after that. Okay, I'm going to change directions for just a few minutes and move on to a different movement of the Earth. So let's take a look at the way the Earth goes around the Sun. So which of the following best represents the path that the Earth takes around the Sun? Is it A, a perfect circle, B, an ellipse, or C, a bow tie? If you chose B, you're correct. The Earth takes an elliptical orbit around the Sun. Now, this ellipse that I've shown here in this little quiz, that's probably a little bit too flattened, but I just wanted you to make sure you saw the difference between a circle and an ellipse. So what is the motion called when the Earth goes around the Sun? A, rotation, B, revolution, C, orbit, D, B and C, or E, all of the above? If you chose D, you're correct. You can call it revolution or orbit. Both of those terms are correct. If you take a look in your manual on page 5.1, you're going to see two shapes on that page. What do you call those two shapes? And what did you use to determine the difference? Now, this is going to be what we look at in lab on Wednesday. So let me just talk you through some of this. So the shape is called an ellipse. But what is an ellipse? Well, that's an ellipse. This is an ellipse. This is an ellipse. There are a lot of different things you can look at which are called ellipses. But how do you characterize an ellipse from a circle? Well, let's pretend that we are drawing a circle. And I'm going to take a thumbtack and push it down. Well, let me back up. I'm going to take a string. I'm going to tie it around a thumbtack and push it into a sheet of paper. I'm going to take the other piece of string and draw it or tie it around my pencil and then draw a circle completely around that thumbtack. That will be a perfect circle. That thumbtack is also called a focus. A circle has only one focus. There's only one point from which the circle is drawn. And every other point on the edge of that circle is equal distance from that thumbtack. Then you see on this slide, it says eccentricity equals 0. Well, do you remember oblateness and how if a sphere is a perfect sphere, it has 0 oblateness? Well, now we are looking at an ellipse. And if an ellipse has 0 eccentricity, it is a perfect circle, not an ellipse at all. So it's the same concept, but different words. And that's because we're not looking at a three-dimensional shape anymore. So let's look at an ellipse. If I were to draw an ellipse, I would take 2 thumbtacks and maybe put them, I don't know, 5 centimeters apart. And I would take a piece of string and just then just tie it in a circle. But now I'm going to take my pencil, put that string around both thumbtacks together, and then draw my circle. This will make so much more sense when we're in lab, I promise. But now we have 2 foci. We have 2 different points that are pulling at our pencil. So you have one major axis and one minor axis. So you have an eccentricity that is now greater than 0, but less than 1. And guess what? If an ellipse has an eccentricity of 1, guess what shape it is? A straight line. So, looking more at eccentricity, eccentricity describes the shape of an orbit. And mathematically, if you want to solve this, you take the distance between the foci and divide it by the major axis. In other words, the longest 2 points in your ellipse. And then you figure out the eccentricity value. Well, in a circle, the distance between the foci is 0. So 0 divided by even the 5 centimeters that I suggested is 0. Trust me, when we're in lab, not on Monday, but in lab on Wednesday, this will make much more sense with our activity. So we have a counterclockwise revolution. So the Earth is rotating counterclockwise. It is also revolving counterclockwise. And sometimes people ask about, especially little kids, they'll ask about the seasons of the Earth. And little kids will think about it, and they'll often tell you, well, we're probably hotter in the summer because we're closer to the sun in the summer. Or we're cold in the winter because we're so far away from the sun. That's actually not true in the northern hemisphere. In the northern hemisphere, we are closer to the sun during the winter time. Actually, in January, we are closest to the sun. But the tilt of the axis is away from the sun. And that's actually what makes it colder. Whereas in July, in the northern hemisphere, we are further away from the sun, but our axis is tilted towards the sun. That's why we're so much hotter in July than we are in January. It's just the tilt of the axis. So, what is the average distance from the Earth to the Sun? Well, it's 150 million kilometers to get from the Earth to the Sun on any average day. And what is that called? What is that 150 million kilometers called? In science, we call that 1 astronomical unit, or 1 AU. Well, how long does it take for the Earth to revolve around the Sun? It takes about 365.25 days, or 1 Earth year. But here's a question. What do we do with the extra 1/4 of a day? What do we do with that every year? Because we do. We have an extra 1/4 of a day every year. What do we do with it? You're going to see that question come up later on. So what are some other motions of the Earth? Well, let's take a look at the pyramids of Giza. Those pyramids were built perfectly to align with north. And north, perfect north, is to our North Star Polaris. However, today they are not aligned with Polaris. So what happened? Well, the pyramids were built roughly 2,500 years ago. Why aren't they pointing there? So the Earth not only rotates and revolves, it also precesses. And so what is the precession evidence? Well, if we look at historic star charts, they tell us that 2,627 north was between Thuba and Draconius, if you look at these pictures on the side. And 2,467 north was at Kochab, and that's a star in the Little Dipper. I just realized you cannot see all the stars that I just listed. But what I'm trying to explain is that it no longer pointed directly to the North Star, which we know as Polaris. And so precession is kind of an Earth wobble. And it is created when forces act on a spinning body. So it's not just on the Earth or the other planets. It also happens with a top. If you spin a top on a table, you'll see that the top of the top will wiggle or wobble back and forth, back and forth. That is precession. And what force is acting on the Earth to cause it to precess? Gravity from the sun, gravity from the moon, as well as some gravity from the other planets. So how long does it take the Earth, just like a top, to precess back and forth? When it goes from Polaris to Vega back to Polaris, it takes 26,000 years. So it takes 13,000 years for it to go from Polaris to Vega, and those are the two stars. Polaris is the North Star, but in 13,000 years from the time that that the pyramids of Giza were built, our North Star will be called Vega. And then it'll take another 13,000 years to go back from Vega to Polaris. I bet you didn't even realize that. All right, so what are the other motions of the Earth? Well, we do have an additional wobble known as the Chandler wobble. And the Chandler wobble is just due to the fact that the weight on the Earth is unbalanced. So we've got 71% ocean and we are only 29% land. And so the Earth is unbalanced. And so the Chandler wobble is just that tiny little wobble that is caused by an unbalanced weight on the Earth. And very large events like the Indonesian earthquake and tsunami in December of 2004, there was a mass shoved inward during subduction, and it actually changed the Earth's rotation and caused the Earth to wobble slightly more. It made the Earth rotate faster by which means it shortened the day. So a faster rotation, but a shortened day of 2.67 millionths of a second. And that was how large that earthquake and tsunami of 2004 was. So, last thing, what else is rotating? Our entire galaxy is rotating. So is the sun. The sun rotates and it revolves. The galaxy rotates in a clockwise direction. It takes the sun 200 million years to orbit the galaxy, or to revolve around our galaxy, taking us with it. So yes, even though when we sit in our desks or we take a walk outside, we might not feel like we're in constant motion, but we are. And I hope you guys have a wonderful day, and I will see you at lab, and lab will make these things a lot clearer for you. Thanks, guys. Bye-bye.